So, since we're going to be working with ODEs, we're going to see a lot of derivatives. And then to deal with these derivatives, and be able to take Laplace transforms of the derivatives, we're going to use some formulas that I'll write on the screen in a second. But just so you know what I'm talking about, when I say derivative, I mean that we're looking for our y prime, our y double prime, so on and so forth. If we use Laplace transforms in ODEs, we will definitely need to know how to take Laplace of y prime, for example. So suppose there's some function f that has derivatives, f prime of t, f double prime of t, so on and so forth. Then, if I want to take Laplace of any of those derivatives, and I'm going to write the formula for the nth derivative, what I'm going to do is I'm going to start with s to the power n, and that's multiplied by the Laplace of f. Then I'm going to subtract s to the power n minus 1 and multiply by little f, evaluated at 0. And I'm going to follow this pattern. I'm going to keep decreasing my powers of s and increasing my derivatives of little f until I run out of s's. So I do s to the power 1, then s to the power 0, and when I'm at that point, I've used up to the n minus 1th derivative of f evaluated at 0. And again, for L of f being capital F, and these quantities f of 0, f prime of 0, so on and so forth, we're just going to find those from f and its derivatives evaluated at 0. So a couple things to note here. First of all, something neat about Laplace transforms is that they're taking Laplace of a derivative, so the operation that is a derivative, when you throw it through Laplace transform, it becomes multiplied by powers of s. So it's going to help us by being one of those methods where we can take derivatives and turn them into algebraic problems. It's quite helpful. Another thing to note is that this formula for a derivative is going to require that we know f evaluated at 0, which I hope is reminding you of our initial value problems where we're always given y evaluated at 0. And then for higher order problems, we ended up getting y evaluated at derivatives in 0. So this is a really nice fit for an initial value problem. It would be a lot harder to solve for just a generic ODE. But before we get into that, we can just do a really quick example of just how you implement this formula, because I do know that seeing all these n's can be intimidating. So let's talk about how we would take L of y triple prime. So in this case, that's the third derivative, so I'm going to start with s to power 3. And I'm going to multiply that by Laplace of my variable, which I'm going to denote by capital Y. And then I'm going to subtract s squared and multiply it by my variable, y, evaluated at 0. Then I move down powers s, I go to minus s. I've already used y of 0, so I have to go up to y prime of 0. And then I subtract, going down more powers, but since I'm at s to power 1, there's no more s left. S to power 0 is 1, it disappears. And so I just have y double prime of 0 by itself. To see another example, let's think about L of y double prime. So this is when we have second derivative. That means I'm going to start with s squared multiplied by y. I go down a power of s multiplied by y of 0. Go down again, but that means that s goes away, and I go up one more derivative of y to y prime of 0. I'm going to also write out L of y prime. And maybe real quick, see if you can figure this out for yourself. So this is a first order derivative. That means we're going to take s out front to power 1 multiplied by y. But remember, we keep going down in powers until we reach a constant, so we're not done yet. We have to subtract s to 0, or 1, times y of 0. And that's how we do this. Maybe make a symbol in your notes. You're probably going to want to refer back to this. We don't often go higher than third order derivatives, so these are the ones that you're going to need. And I also want to note kind of a way to check as you're doing this minus thing, whether you're doing it right. Your last initial condition is always one derivative lower than the transformed derivative. So if I'm taking Laplace transform of third derivative, the last initial condition I write should be one below its second derivative. When I did Laplace of second derivative, my last initial condition was first derivative. And when I took Laplace of one derivative, my last initial condition had no derivative. So that's just like a quick way that you can check that nothing's gone wrong when you start working through this process. Okay, let's go ahead and also write out the steps for solving an initial value problem with Laplace transforms. I think we can do it relatively quickly, and I like it when all the examples have their own videos. I don't know how you all feel about it. So, we would like to use Laplace transforms to solve initial value problems. The way we're going to do that is following 4 simple steps. So first, we're going to take Laplace transform of both sides of our ODE. So remember that L of y is going to be denoted by capital Y. We're going to remember to use linearity whenever necessary. And we're also going to need to remember that derivative property for however many derivatives we have, that s to n y. Where we always end subtracting the initial condition of one lower derivative. And here I just want you to be careful, make sure that you plug in your initial conditions. So you want to actually have a number instead of y of 0. That'll make it look much easier. Then, after you've taken Laplace of both sides, you're going to set both sides of your Laplace transforms equal to each other. And at this point, you should make sure that there are no y variables or t variables left over. What you should have is an algebraic equation with powers of s and with no derivatives. So we've managed to get rid of derivatives in our initial value problem and turn it into this algebra problem about s. Then you're going to go ahead and solve for big Y equal to some stuff. You're going to isolate that variable y. And our last step is just to take the inverse Laplace transform, sort of undo everything that we introduced. And you're going to do this on both sides of that thing you found in 3 that isolates y. So you'll have L inverse of big Y is equal to L inverse of whatever that other stuff was. That's going to give us the solution y of t equal to something. And at this step, the only thing to be really careful about, I guess again, you really want to remember to use linearity as necessary. Generally, the way you solve this at first looks very messy. You have to split everything up so that you can take inverse Laplace transform of functions that look like things you know the rules for. And then again, we want to make sure there are no s or capital Y variables left over. So after we take inverse Laplace, we should be back to having little y and t, the variables that we're thinking about. So those are the steps. They can just get a little bit long, like the algebra or the inverse Laplace step. We'll look at a lot of different cases of that. But overall, I think it's a pretty simple framework, even if the steps can get complicated. So I'm going to pause, move to the next video. Please take a pause if you need to finish writing some things down.